Advanced Algebra Functional and Graphical Reasoning, Standard 4.3. I'm going to look at what the definition of a graph is. The graph is something that we've all heard of, but not everybody can define. It's simply a picture of all solutions. That's it. It just physically shows you all the ordered pairs that makes a particular function true. So we have this family of functions that we're going to look at here. This is a radical graph, or what we call the square root graph. Y equals the square root of x. And 1, 1 makes this true, this green dot. Because if you put 1 in both the x and y positions, you have a true sentence. 1 equals the square root of 1. Likewise, 2 equals the square root of 4, and 3 equals the square root of 9. But notice the shape. This is called the parent function for this graph because it's the simplest version that we base every other graph on. Domain and range, you're going to hear often with graphs. Domains are all possible x values covered by a graph, leftmost to rightmost. Range is all y values covered by a graph, lowest to highest. Okay, so for example here it says graph, tell the transformation from the parent and provide the domain range. Okay, so there's another video you can watch on all the transformations. And one that's very common is if you add on the outside of a function, it goes up. Okay, so notice that I have the parent graph here, and the new graph is that same picture up 3 units. Okay, so this works on your graph transformations. The transformation will be a vertical shift up 3. Again, you add on the outside. You start at the point 0, 3, and this is helpful. You can get 0 and 3 by looking at the function, change on the inside. There's nothing to change here. There's nothing being added, so 0. Don't change on the outside. That 0 and 3 shows up in the domain range. In inequality notation, we say the domain is x greater than or equal to 0. The reason for that, think of all the x values covered. Leftmost, it goes to 0. We read only this axis down here. And it goes forever to the right. In interval notation, that's bracket 0 to infinity, meaning that 0 is the leftmost boundary. Again, read only the x values. The bracket means you can be equal to 0. And then infinity is the idea of going forever rightward. Okay, infinities always get parentheses. The range uses this blue number. Range is lowest to highest. So we read only these numbers. I go down to 3, including 3. So I put a bracket 3. I go upwards forever. Or you can say y greater than or equal to 3. Second example, same instructions. Here we got a little bit more going on. So again, remember your transformations. Subtract on the outside, you go down. Subtract on the inside, you go right. And this 2 is a vertical stretch. Okay, so here's the picture. You went right 1, you went down 5, and it's noticeably stretched or steeper than the blue graph. The blue graph against the parent. Okay, there's that information. The starting point this time is 1, negative 5. Change on the inside, not on the outside. Notice this 2 has no bearing on that. The domain goes left to 1, looking at the red graph, reading only the x-axis, left to 1, right forever. And the range goes down to negative 5 and up forever. Third example, same instructions. Again, a bit more here, or quite a bit going on. We're adding on the inside, that goes left. We multiply by a number less than 1. That's a vertical shrink or vertical compression, some say. And this negative here is going to reflect it or flip it upside down. Okay, so you see that here, noticeably flatter. That's from the 1/4, leftward 1 from the starting point, and clearly upside down. Okay, sometimes you hear the word reflection x. You have to be careful with reflection x. Sometimes the word upside down will be better, but here, because we have no vertical shift, it truly is a reflection of the x-axis. Notice this time the starting point is negative 1, 0. Again, there's adding nothing on the outside, and this number has no bearing on that. The domain doesn't seem to care that it's upside down. It's still left to negative 1 and right forever. But the range is noticeably altered because this time we're going down forever. So we must put our small value, in this case what we call negative infinity. It has to be listed first. If you ever see negative infinity, it's always on the left. It would never be on the right. Just as you never see positive infinity on the left. So you go down forever and up to 0. Again, range reads only these numbers. Okay, we also have the cube root of x. Okay, notice it is two-sided. And the reason it doesn't abruptly stop like the square root is, you can take negative values inside a radicand if there's an odd index. The cube root of -1 is -1. The cube root of -8 is -2. Okay, if you multiply in the negative number an odd amount of times, it's negative. So the odd index radical here will take the negatives and go both two-sided. Same instructions as before. Here's simple shift upward. But notice the domain and range difference. This time it goes left forever and right forever. There's no restrictions, no abrupt stops. Also goes down forever and up forever. These are very common, domain and range. What you could also say is all real numbers here. Fifth example, graph, same instructions. Again, the point here is going to be 4, 3. Again, you go up 3, right 4, vertical stretch. The domain, all real numbers, range, all real numbers. There's a look at the graph. The red this time is the parent. Notice you are right 4, you're up 3, and there's a noticeable stretch. The instructions here, analyze and graph, or the standard rather, analyze and graph radical functions.